Hi students, welcome to my lectures on chemical reaction engineering. In today's lecture, we are going to discuss about the temperature dependency of two parameters. One is rate constant, second is equilibrium constant. Because the temperature dependency will be different for the equilibrium constant and different for the rate constant. Let us see with a small example that if I increase or decrease my temperature, how my rate constant as well as equilibrium constant will behave. Let us first take the case of rate constant. A gives rise to B, B gives rise to B. It could be a reversible reaction or irreversible reaction. Anyway, the temperature dependency of the rate constant will say only one thing, that always the temperature, if you increase the temperature, the rate constant always increases. If you decrease the temperature, the rate constant value always decreases. Whether it is exothermic reaction or endothermic reaction, the dependency is always the same. For example, for the first rate equation, rate constant for the forward equation is equal to pre-exponential constant into exponent of minus delta E1 by RT. You know, T is the temperature or is the universal gas constant, and delta is the activation energy for the first forward reaction. Similarly, K2, the rate constant for the backward reaction is nothing but pre-exponential constant into exponent of minus delta E by R into T. Delta E2 is the activation energy for the backward reaction. Let us take a small example that if you increase the temperature, what happens to the rate constant? Given pre-exponential constant for the reaction 1, forward reaction is 9 into 10 power 14 per second, because it is a first order reaction. K2, K02, that means pre-exponential constant for the backward reaction is equal to 12 into 10 power 14 per second. Activation energy for the forward reaction is 25,000 calorie per mole and the backward reaction is 30,000 calorie per mole. The gas constant is 1.987 mole per calorie per mole Kelvin. Okay? And using these equations, let us find out at 25 degrees centigrade what is my rate constant value for the forward reaction. If you substitute all the values in this equation and temperature is 25 degrees centigrade, then you get the rate constant value for the forward reaction is 4.2 into 10 power minus 4 per second. Similarly, if you substitute all the values for the backward reaction, K2, you get 1.22 into 10 power minus 7 per second. That means these two are the values for the 25 degrees centigrade. Let us calculate the same rate constant values at higher temperature, which is 100 degrees centigrade. And if you substitute everything remains the same, that is pre-exponential constant is the same, activation energy is the same, R is the same, only T is going to change. T now it is 100 degrees centigrade. Now if you substitute every value in this rate constant, and the K1 you get is 2.04 per second, K2 is equal to 2.72 per second. Now you see the relationship. As you increase the temperature, the rate constant values were increasing. Okay? If you decrease the temperature, if you start here and come down to here, that means if you decrease the temperature, the rate constant value decrease. That means for the case of rate constant, if you increase the temperature, rate constant always increases. If you decrease the temperature, rate constant always decreases. That is what I have shown it through arrows. Increasing temperature, increasing the rate constant value. Decreasing the temperature, decreasing the rate constant value. And let us take the case of equilibrium constant now. Now you know A gives rise to B, forward is K1, backward is K2 rate constant. Equilibrium constant is defined by product of all the product of concentration of all the products divided by product of concentration of all the reactants, with respect to their rates. And for this case, the equilibrium constant Ke is nothing but K2 by K1, which is nothing but CBE by CAE. Okay, CB is the equilibrium concentration of B, CAE is the equilibrium constant of A. As we have discussed in the lectures of the reversible reactions, in case of reversible reactions, reaction won't be complete, okay. It will stop at somewhere. Where exactly it stops, who will tell? The equilibrium constant will tell, okay. The equilibrium constant value will tell exactly at what point the reaction should stop. At that stopping point, the concentration of B is nothing but CBE. At that point, the concentration of A is called CAE. That means, and see what happens, more is the rate constant value, more is the product, means because product divided by reactants. If K is more, the product is more. K is less, the product is less. That means if you increase the rate constant value, the concentration of the product will increase. If you decrease the rate constant value, the concentration of the product will decrease. And important thing is, I told you reversible reactions stop at some point. At some point, that means a equilibrium point, okay. The conversion at that point is nothing but Ke by 1 plus Ke. You can get this derivation in my previous lectures, okay. That means if I know the equilibrium constant value, that means I know what exact conversion, that means at what point the reaction will stop, will not further move forward. And let us see that using a line representation. A line is connected by the two dots, because slowly we are moving towards the temperature dependency. Here at this point, that is more concentration of A, less concentration of B, typically start of the reaction. At this point means at the end of the reaction, that means at end of the reaction the concentration of feed is low, product is high. At this point, less A, more B, here more A, less B, and reaction will stop at some point, that is this point. At this point, the conversion is XE, the concentration of B is CBE, the concentration of A is CAE. That means more is the equilibrium constant, the point will shift towards this side. That means if the point is shifting towards this side, means more product and less reactant. If the point is here, that means more reactant, less is the product. That means more is the rate constant, more is the equilibrium constant, more is the product formation, less is the equilibrium constant, less is the product formation, okay. Let us take a small example. I told you in the normal rate constant, temperature dependency is linear. That means if you increase temperature, the rate constant will increase, decrease the temperature, rate constant will decrease. Here it will differ, okay. For exothermic cases the relationship is different, for endothermic cases the relationship is different. Let us see with a small example so that you will understand it much better. The base normal case, at 100 degrees centigrade the equilibrium constant is given as 0.5. If equilibrium constant is 0.5, what is my conversion? Ke by 1 plus Ke is nothing but 0.33, which is 33%. That means if you know the Ke, you know the conversion. For this case, example, a random reaction, 33% conversion is possible. If I decrease the temperature, that means at 100 degrees centigrade the conversion is 33%. What happens if I reduce the temperature now? For the two cases, one is exothermic case and second is endothermic case. If I reduce my temperature, what happens to my equilibrium constant and what happens to my conversion? From the thermodynamics, because rate constant depends on temperature, that relationship you can get from the thermodynamics. The equilibrium constant depends on temperature as well as pressure. Let us take the case of only temperature today. The relationship between the rate constant and the temperature is given by Van't Hoff equation. The Van't Hoff equation says that ln of equilibrium constant 2 divided by equilibrium constant 1 is equal to minus enthalpy of the reaction divided by R into 1 by T2 minus 1 by T1. That means if you know the equilibrium constant at one temperature, you can estimate the equilibrium constant at another temperature. For the base case, I know the equilibrium constant is 0.5 at 100 degrees centigrade. And for the exothermic case, what is my equilibrium constant and conversion? Simply, I will use this equation to predict my new equilibrium constant and new conversions. For exothermic case, you know the enthalpy reaction is negative. That is why delta H is equal to minus 50,000 calorie per mole. R is given, T2 is 25 degrees centigrade, that is lower temperature, and T1 is 100 degrees centigrade. If I reduce my temperature, what is my new, if you substitute every other parameter in this equation, you get the equilibrium constant is 2.92. Earlier my equilibrium constant is 0.5. Now my equilibrium constant is 2.72. That means by decreasing the temperature, I have raised the equilibrium constant value. If I increase the equilibrium constant value, what happens to my conversion is increasing, because now it is 0.73, earlier it is 0.33, now it is 0.73. That means for exothermic reactions, if I reduce the temperature, my equilibrium constant will increase and my conversion will increase. And same case let us do for the endothermic reactions. Same base case, here is 100 degrees centigrade, here is 25 degrees centigrade, and delta H is positive. Now here the delta H is negative because of exothermic reaction, here the delta H is positive because of endothermic reaction. If you substitute the delta H value, R value and temperature value in this equation, you are going to get equilibrium constant at 25 degrees centigrade is 0.0916. That means equilibrium constant value has been come down. Okay, here exothermic, the equilibrium constant has been raised. For endothermic, the equilibrium constant value has been dropped down. If the equilibrium constant value is dropped, that means the conversion will also drop. Here the conversion is 33%, here the conversion is 0.08%. That is what this behave in a opposite way. In very simple sense, for case of exothermic reactions, if I decrease the temperature, equilibrium constant rise, therefore the conversion rise. For case of increasing temperature, the equilibrium constant will decrease and conversion will decrease. That means if you take this as a high temperature, this is as a low temperature, that means low temperature, this is a high temperature. By increasing the temperature, you can see what happened, the equilibrium constant has been dropped and the conversion has been dropped. So you can take this way, right? Here for endothermic reactions, decreasing the temperature will decrease the equilibrium constant, and so the conversion will drop. That is what we have seen. And if you increase the temperature, the equilibrium constant will increase, so therefore the conversion will increase. This is what the basic difference between rate constant and equilibrium constant. Here there is nothing about enthalpy of reaction, it is always my delta E. Here the positive and negative sign will come. Delta H is negative, so that in the equation it will become positive. Okay, here the delta H is positive, in the equation it will become negative. This is what the basic difference that comes when you talk about the equilibrium constants. Hope you have learned, and let us meet with the new lecture.